All right, today or this week, the focus of our activity is on P and S wave travel times and stuff like that. There's a couple of resources. I'm going to go over it so you can either watch the video, which apparently you are now. But there's a slideshow, I think, or maybe it's a PowerPoint. I can't remember if I ever converted it over. It's a PDF that walks you through what I'm going to show you how to do. So in case you need more refreshment or practice, or you don't remember what I said and you don't want to watch me, drabble on, that's available for you this week. And also, let's see, there was, oops, I just got a 404 error. That's funny. And then I think there's the P and S wave travel time thing, which looks like this when it's in color, that you can either have printed or you can use it on the screen. Just know that on your quiz and on your test, when you get the questions, it just like, the other tables, it'll be presented. So you might want to practice doing it on the screen. Or if you have it printed out, then keep it in your notes. So when you take your test, you can do it there. So that's that. And then I will also talk about the optional lab activity today. And we'll go through a little bit of that. But before I get started, I want to actually talk about the extra credit opportunity. So this extra credit, it's worth 10 points. It does require you to have stuff, but you can use your imagination as to what you use. So the idea is to give you extra credit for obviously doing extra work, but more importantly, it's to prep you or prime you for the final lab activity. So your final lab activity is called Models of Geography, and you're going to create a model using stuff around your house. I used to limit it to food, but you can make it out of anything you want, really. It used to be a way for us to have a potluck and me to say I wasn't having a potluck. It actually started in Victorville. Well, I'm not sure. I used to teach high school and I wanted to have a potluck for my students at the end of the semester, and they said I couldn't. So I said, well, what if I had them model earth science using food? And then it was all stuff we could eat. So, we had leaf litter, which was made of potato chips, and we had cakes that were in the shape of plate tectonics or faults and things like that. And people got pretty creative. And I had come from one of those, and I used to teach in Victorville. So I taught high school, and then I'd leave high school, and then I went up to Victorville twice a week. And I was talking to my students. I was totally sugar rushed because I had spent, 4 hours of my day eating nothing but sugary snack stuff. And I didn't bring lunch because I wasn't hungry. And they're like, gosh, Pitts, you were crazy today. I go, I know, I have this total sugar high. It's insane. Now I know why you don't give sugar to children. Anyways, they're like, what were you doing? And I told them, they go, we want to do that. And I was like, all right, if you wanna. So I turned it into a lab. And so this is an example. You can't do it for your final model lab. You can either model something or you can do a process. So this is showing you how to do a process using food. So I wanted to take a couple of minutes and explain what that means. So and some of the options that you can use instead of what it describes. So kind of what they're trying to get at. And then so let me share my screen here. So I'm going to share the first one. Both of them that are up there, the same. It's just that one of them says to use Cool Whip, the other one says to use frosting. But I'll explain what you need. So you need something that's going to model the asthenosphere. Now, the asthenosphere is what the plates sit on. It's considered a semi-solid, so you don't have to make it a semi-solid. Cool Whip is technically a semi-solid. Once it gets kind of warm, it oozes and is no longer solid. But the asthenosphere is more like if you ever made that slime for your kids made out of soap and glue and stuff. you know, it holds its shape for a while, but after a while it flattens back out. That's like the asthenosphere. And that's what the two types of plates, continental and oceanic plates, sit on and create all of the interactions. So there's like convergence where they come together, there's divergence where they come apart, and then there's transform where they slide past each other. So you need something to model the asthenosphere, something that the plates is sliding on. So Cool Whip, one of them says frosting. You can use jam, jelly, you know, something that's liquidy, that's gonna like ooze. It's got to be able to like press into places, but it also needs to be able to hold its shape enough that you can see one of the interesting things about divergent plates is when they pull apart, you get essentially like stretch marks. If you look at the middle of the Atlantic Ocean in Google Earth, you'll see like these like long scratches almost. That's the plates that are kind of pulling apart. It creates this like striation on the ground, and you'll actually see that if you use, definitely if you use frosting, because I used to bring all the frosting in. But apparently you can do it in Cool Whip too. I've never done it in Cool Whip. I know students have done it in Cool Whip. It will not work with the foam whipping cream that comes out of the thing. It doesn't hold its shape long enough. Cool Whip is, you know, relatively shelf stable. It's really bad for you. Although I used to eat it by the spoonful as a kid. So mayonnaise, people have used mayonnaise to do it. So anything that's going to be the asthenosphere. And then you're going to need something to model the lighter continental plates. In this case, they recommend using crackers like graham crackers. I've seen people use saltine crackers, you know, some sort of like cookies would work. If you had like a cookie, that would work. And then something to model the more dense oceanic plate. And in this case, I think they suggest using fruit roll-ups, but you could use, I don't know, a piece of lunch meat, salami. Oh, that is a piece of lunch meat. So something to model that. You want them to be rigid because they are, so they, you know, but not too rigid. I mean, I guess salami would work better than turkey if it's thin sliced deli meat. You know, you want something that's going to be able to, you're going to be able to pull it apart across these things and it's not going to like shred. But the idea is that for the extra credit, what you do is you take pictures of yourself or somebody else modeling the different types of plate interactions. So ideally you'll have like, I think 4 pictures, one of divergent plates that are both continental. So you would need, you know, 2 pieces of cookie or 2, like a graham cracker cut in half. And then 2 plates that are converging that are continental, 2 plates that are converging that are oceanic, and no, not that oceanic, oceanic and continental, sorry, convergence, and then just transform, they're sliding past each other. So there's like 4 pictures that you would turn in, and then, you know, you can answer these questions. The idea is to, you know, kind of gear you up, like I said, give you extra credit and gear you up for thinking now about what you're going to do for the Models of Geography lab, which is due the last week of class. So, so just to kind of start looking around at what you've seen. One of the most interesting I've ever seen, and is that you know, when we used to be in person, people would bring stuff in. I've seen, you know, like lasagna turned into fault lines, which was really kind of clever. I was like, wow, that's kind of cool. So they made the layers like a normal fault. So I was like, wow, that's kind of crazy. So part of the lasagna was taller than the other part of the lasagna. I was like, very interesting, very clever. I don't know how they got it to stay, but it managed to kind of look appropriate. But one of the more interesting ones is somebody brought in what I thought was just a model, not of the process, just a model. And it was like a volcano made of popcorn. You know, they'd like packed all this popcorn on the outside. And I was like, wow, that's pretty cool. Because your 2 options are, you can either do a model, the layers of the earth, like or soil in a cup or something like that, which is by far the most popular. And in my opinion, I'm so tired of seeing it, but I love you all so much that if that's what you got, fine, I will give you the credit for it. So I, I'm going around the class. This was at Fullerton, so I'm going around the class looking at everybody's models and they're showing me their process, and I'm, giving them feedback, and they're talking about their model, because you have to say, this is showing, so the whipped cream is the Asthenosphere. I used whipped cream because it, provides a semi-solid that the plates can slide on. I used graham crackers because it's less dense and holds its shape a little better, so that when I had the convergence, that actually created a convergent boundary when the two of them come together. And so they're talking about that, and all of a sudden I hear pop, 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 pop. They had actually brought in a sterno in one of those little single egg skillets, and they had put it inside, and out of this cinder cone volcano came popcorn. I was like, that is awesome. So that brought up the idea of, okay, whoever has the most awesome one gets extra credit. And then we hit COVID, and that kind of changed everything, because now, you can't, sit there and model everything, and you don't want to pop, a whole bag of popcorn for everybody, because, we all kind of, are far apart, so you can't really share food. So now, and I'll talk more about this in a couple of weeks when it's the end of the semester, you could create like a slideshow, you could do a video, or you could present it live, and I look at them all equally. So whichever idea is the most awesome gets extra credit. So just keep that in the back of your mind. So anyways, this one is snack tectonics. It's a process. So if you do it and you turn in the 4 pictures, then you get the extra credit. But any questions on the extra credit? That's optional this week. And really, you can use, you can say, you can really use pretty much well, not anything, but hopefully there's, stuff around that you can use to model these things. The one that needs to be no, you could figure it out. You could make it work, even with 2 different types of cookies. You could make it work. So just use what you got. Don't do anything special. Just use what you have. You could use a bar of soap and something else. Just be creative. Think outside the box, so to speak. All right. So that's the extra credit that's available this week, and you'll have until the 18th to turn that in, and that will not. You can't turn it in late. So if you're gonna do it, just get her done. And the other one is the same. It just says to use frosting instead. I mean, they're the same lab. It asks you to do the same stuff. It's just you get to use frosting, which is how we did it in class. So, all right. So let's talk about P and S wave travel times. So I'm going to switch to my other thing. Oh, you're going to need this fancy chart thing, so you can leave that up on your screen, and then this worksheet, which is this guy. Wait, let me show this, that guy. Switch modalities here. Hopefully, new share. There we go. Okay. All right. So, all right. So the first thing it talks about is converting to and from scientific notation, and it's kind of an afterthought, but I put it in here because you may run up against this at some point, and so I wanted to make sure that I, at least talked about it. So scientific notation is just a way to write really big numbers or really small numbers, not using a lot of space. So, and it's all about moving the decimal point. So for example, this 4, you start by writing the number that you have. Oops, I can't see what you see because I put the Zoom window in the, there we go, put you over there. So you put down the number that is before the thing, and then you add however many zeros it says. So it says 3 zeros, 1, 2, 3. Okay. So that one's easy. Now, if it's a fractional number like this, a decimal number, fractional. A decimal number like this, again, you put down the number, and then I always put down the 3 zeros just so that I keep it the same. And then this time I'm going to move the decimal 1, 2, 3 places. So that's just the way I like to do it. So it says how many zeros I have, and I just keep that. So if it said, you know, 9 to the 10 to the 9, I would write down 9 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9. And then I can come back and put in my commas. And that's a $9 billion. Right? So that's just how I've learned to do it. The other way to do it is to, you know, write the 9 and then move the decimal 9 places. But then what am I moving it? I'm moving it through air. So I always just told myself as a kid, just put however many zeros it says here, and then move the decimal after you're done, like I did for this one. Okay, and then the other one is, of course, going to be the opposite. So converting it from a big number. These aren't big numbers, but from this number into scientific notation. So let's see. We start by writing the number. And this time we're going to move the decimal until it gets in between these two. So we end up with just a whole number with no zeros. So we have to move it 1, 2, 3 times. So this would be 5.6 times 10. To the 3. Sorry. Cough. That 3 is ugly, but it's a 3. I promise it's a 3. It doesn't look like a 3, but it is a 3. Okay. So anybody want to give a guess as to what B is? While I go get a drink of water, because I'll be back. I'm not going anywhere. I'll give you some thinking time. When I come back, you can either put it in the chat, or you can say it out loud, or I'll just say it out loud if you don't want to say it out loud. But I gotta get some water because let's see here. All right, so 1, 2, 3, 4. 1 times 10 to the 4. Hey, I like the little carrot. Dang, yeah. You people have been like at home too long. You know how to use carrots to show raised to the 4th power. I never knew that when I was your age. You're like, you are my age. All right, so that's how that works. So now we're going to get into filling in this chart. And in order to fill in this chart, we're going to need this P and S wave thing. And I'm going to use a bigger one. It's the same thing. It's just bigger, so it makes it easier for y'all to see as we talk about it. But it's the same chart. So a couple of things about P and S wave. So P stands for primary wave. It's called that because it gets there first. And S is secondary waves. They're also called surface waves. It gets there second. It takes longer to travel. P waves will go through liquids and S waves won't. So this is also known as a shear wave. And that's because it moves opposite of each other. So P waves are compressional waves. They kind of move like if I shook a slinky, or like any wave like you've ever drawn, you know, it moves. P waves move like up and down and up and down and up and down. So what happens is that, oh, sorry, that's not true. Sorry, that's an S wave. Sorry. P waves move side to side. So it's like if I took my slinky and I pushed on it, then this part of the slinky would hit this part of the slinky, which would hit this part. So what would happen is I would have part of my slinky be close together, and then eventually this part where it's close together would move, you know, continue to move this way. So that's a P wave, or a compression wave. Okay, and then there's the S wave, which is a shear wave. And that's one, sorry, that moves side to side. So it moves like this. So there's no like connection between this molecule and this molecule. So they're not like pushing each other. So if you were in a swimming pool, it would be the difference between pushing the water at somebody and moving the water side to side, right? Eventually, yeah, they'll feel it, but the S waves don't travel well in, I mean, it, you know, they may not feel it at all. It'd be like pushing the water this way, and the person in front of you doesn't like feel it. And that's because it's a shear wave. And so that's why it doesn't travel well through liquids, because the molecules aren't connected. They're not bouncing against each other in a direction, like in a forceful direction, I guess. I don't know how to better explain it, but anyways, there it is. So, so for our purpose, it's important to know that P waves travel faster. They travel at a rate, like we know what that rate is. And so based on the arrival time, the difference in arrival time, we can figure out how far away an earthquake is. And this is what we still use to this day in order to figure out where the epicenter of an earthquake is, how deep the earthquake is, and stuff like that. So obviously, if you're real close to the earthquake, you're going to feel the waves very close together. I am one of those weird people. I love earthquakes. These compression waves are usually the ones that kind of go boom right at the beginning of an earthquake. If you've ever like been in an earthquake, you almost feel like you can hear the earthquake. It's like koosh. And then the shaking starts. The shaking that we feel are these S waves. And the waves that come after them, actually. The other surface waves. This is a shear wave, but there's another type of wave. These are body waves. They travel from the epicenter. And then there are things called surface waves, which actually are really the ones that we feel. But I always feel like there's that little kind of like that crack, and you're like, whoa, I think we're having an earthquake. And then you're like, yep, this is an earthquake. Yeah. So that's what we're going to talk about this week, is calculating where earthquakes are based on these arrival times. So we're going to do it a little systematically at first, and then we're going to do it a little more kind of review-ish, because we're going to bring in the concept of scale and stuff like that in the actual lab assignment, which is optional. Okay, so let's look at the first one. It says, fill in the chart below the P wave travel time for an epicenter, a distance from the epicenter of 2,000 kilometers. So what you want to do is you want to go up from the 2,000 kilometers. That's down here at the bottom of my chart, right? I just go up here until I get and hit this P wave, and then I come across here, and this is in minutes. So I would just write 4 minutes. Okay. Now, let's see here. These are in 20-second increments. These are in 20-second increments. And I know that because if I did the math, it goes 4, 420, 440, 5, right? As far as minutes are concerned. These are in, let's see, 1, 2, 3, 4. It looks like 200. So let's see, 2, 4, 6, 8, 10. Yeah. So these are in 200 kilometer, and these are in 20 seconds. Let me make sure it's the same scale on the back. Yes. Yes. Okay, cool. It should be, because I think I just blew this guy up and put him in black and white because I'm cray like that. All right, so let's do another one. Let's look at 11 minutes and 20 seconds. So this time I'm going to start at the travel time side, 11 minutes and 20 seconds. I'm going to trace this over all the way to the P wave. And then down. And 8,200 kilometers. 8,200 kilometers. All right. So does that make sense? Everybody good? Yay. I got one good. That's good. I'll go with one good. No, just kidding. All right. So this one over here, the S wave one, works just the same. Only instead of going all the way to the P wave, we're just going to go to the S wave. So it works the same. So, but let's do one. I'll do one in red. And then I'll continue my lecture. And if you want, I can come back and do some more of these with you. All right, so we'll do 12 minutes and 40 seconds. 12 minutes, 40 seconds. This time I'm just going to the S wave. I say this for two reasons. One, so I remember not to keep going. And two, it looks like it's a little bit less, but so it's not really right there. It's actually like a little bit, it's like in between. So I'm going to say it's 4,100 kilometers. Because it's like not like all the way over there. Like it hits the line before it gets to this spot here. So I'm going to say it's 4,100. And then the same thing, 1,000 kilometers. This time I'm going up to the S wave. And again, it looks like it's about a little less than 4 minutes. Say 3 minutes and 50 seconds. You say, gosh, Pitts, that's really kind of like cutting it close there. Yeah, well, I think I gave you 10 or 20 seconds on the answers in the quiz. I'm just kidding. I think I've picked ones that are like pretty darn like spot on a particular number. But if in looking at your quiz, when you get it back, you go, Pitts, that's a little brutal. Like I was off by 10 seconds. Come on, I'll give you the point. But I think I've found all the ones that are splitting hairs over the years. Over the year, sorry. It's not years. It feels like years. It's only been a year. I keep reminding myself it's not going to be like this forever. Okay. So there's those two activities. Right. Now we're going to do this one. So this one's a little different. This one we're going to need another piece of paper for. I'm just going to use like, oh, I can't use this one because I already have it drawn here. So let me erase the back of this faux piece of paper. All right, so now we're going to talk about the difference in arrival time. So first we have to use our travel time in minutes and find how long of a segment we're looking for. So I'm just going to use the side of my little piece of paper here, and it says 3 minutes and 20 seconds. So I'm going to take my piece of paper and I'm going to find 3 minutes and 20 seconds. That's this spot right here. Okay, now comes the hard part. Okay, I'm going to find out where this hits the P wave And this part hits the S wave. So I'm just going to slide this into my little thing here. So maybe a little bit like, there we go. It looks like, then I'm going to trace that line down. Okay. And it looks like we're at 2000. Why did I get a different number last time? Hold on. Definitely not right. 3 minutes, 20 seconds. That part's right. That's funny. I did. I put the marks. I didn't change the marks. I guess it's important to make sure that it's straight up and down pits. My paper's in the way. All right. So we'll say it's 2,400 kilometers. We'll do another one because, like I said, these ones are a little more tricky. So 5 minutes and 40 seconds. 5 minutes and 40 seconds. Obviously, I'm going to start. Actually, let's start somewhere different. Let's start here. 5 minutes and 40 seconds. It's 2 lines past here. That's here. Okay. And I'm going to take this. Find out where those 2 things intersect. And I'm going to come straight down. Here, I guess. Okay, so 4,000 to 4,400 kilometers. That's how that one works. And then the last one is to do the opposite. So this time we're going to figure out, 2,000. So what's the difference in these times here? So we take our little mock piece of paper and it says 2,000 kilometers, right? Okay, cool. We want to know the difference in arrival time. So we're going to look here. We're going to plot this spot here. Oops, sorry. This spot here. And this spot here. So we want to know how much time has allotted between these 2 spots right here. Then I take it down here. And looks like it's 3 minutes. See that? I line it up down here and it's 3 minutes. That's how those ones work. Another way to do this one, which I haven't mentioned, so I'll do it right now, is to just trace the 2 lines over. So it says 2,000 kilometers, right? So I go here, we already have the line, it's here. And then I go from my S wave, which is here, and across to here. And then I just figure out the difference between this blue line that I drawn before and this orange line. And it's 1, 2, 3 minutes. Look at that. Works the same way. Okay. Right. Okay, so I can come back to this after I talk about the locating epicenters activity, if you want. you'll get better with practice, that's for sure. So, all right. So this is the optional one, and this one is recommended that you at least go through it with me and you go, oh, I get that. And then because the quiz might have questions like this. So this one shows you a seismogram, which is what we use, a seismograph, sorry, the thing we use in order to figure out when these things happen. So there are a whole bunch of these, you know, earthquake seismometers, things that measure earthquakes or movement in the earth. And when an earthquake occurs, you know, it happens at a spot and the energy radiates out in all directions. Okay, so it's happening underneath the Earth's surface at some depth, could be close to the surface, could be deep, depends on, you know, what's going on. And that energy radiates out from that space. And so the P and the S waves start traveling and the whole thing. Okay, so this one is saying this is my P wave arriving. So it arrived at 12:21 and 30 seconds. And this is the second wave, which is my shear wave, which arrived at 12:22 and 41 seconds. So in this particular example, it's just talking, you know, it's talking the long way about what they're doing here. Here's another one. This one arrived at 12:22:05 and the S wave arrived at 12:23:35. And the difference, of course, is this one's probably closer to the earthquake than this one because it got there first. So, so the difference between these two is going to be smaller than it is here. So that's why you can't just use one. If the earthquake took longer, you know that the P and S waves diverge. They are not the same. They're not linear distance between them. So it's not the same amount of time if you're this close versus if you're this close between those P and S waves. So it says on this thing, the first set of disturbances, arrival of the P and S wave. The second one is the S wave. Notice that the P waves arrive in the upper sooner than the lower. That indicates the upper station is closer. So this is all stuff I just said. For each station, we can determine the time lag by finding the difference in seconds. That's the important word, between the beginning of the P wave and the beginning of the S wave. So calculate in seconds. The units of distance are in seconds because, oh, sorry, the units of distance, sorry, that's time, is in kilometers because the P and S waves travel at the rate of, P waves travel at 6 kilometers per second and S waves travel at 4 kilometers per second. So 60 miles an hour, 40 miles an hour. Because I always have students go, isn't 4 faster? It's going 4 kilometers faster. No, it's like 40 miles an hour, 60 miles an hour. Which one's faster? This one. Okay. So therefore the distance for these units is in kilometers. Oh, all right. Okay, so looking at this upper P wave arrival time, 12:21 and 30 seconds and 12:22 and 71 seconds, we calculate the lag. So the way I always do it is I go, okay, hopefully if this number is bigger than this number, then that's a good thing because that means we don't have to, that means we're a full minute away. So I go 21 to 22. So 21:30 to 22:30 is 1 minute. And then 30 to 41 is 11 seconds. So a minute is 60 plus 11 equals 71. So just like they said here. And then the same thing here, 22 to 23, that's a minute. And then 30 seconds on top of that, a minute and 30 seconds or 90 seconds. Okay, so once we've done the addition and subtraction and stuff, sorry, yeah, sometimes you have to subtract. Like if this was 04, then, you know, you could either add 2 minutes and then subtract 1 minute, or you can say, okay, well, it's a minute and 59 seconds difference. So then we do a little bit of, you know, math. So we take the seconds, so 70 divided by 8 times 120. So now we have to use a calculator because that's math I can't do in my head, nor would I expect anybody else to be able to do it in their head. No. Does the sticker say it is? No, it does not. Oh, no, it's not. I waited for you to have your Chinese food. Sorry. So 70 divided by 8 times 120 is 1,050 kilometers. And then we do the second one. So 90. Oh, I think I only did 70. Ooh, 71 divided by 120. No, divided by 8 times 120. 1065. Darn it. 1065. It's important to put in the right numbers, Pitts. 90 divided by 8 times 120 is 1350 kilometers. All right, so now please describe the relationship between time lag and distance from the epicenter. Use data from the sheet to explain your answer. So, well, I don't want to just give you the answer. I mean, I could, but I don't feel like anybody's learning if I just tell you the answer. Does anybody want to try for the answer, or do you want me to just give you the answer? There's a message. Okay, easy it is. All right, so as lag increases, the distance from the epicenter increases also. Oh, using data from above. The first station lag was 71 seconds, and it's 1,065 kilometers. But the second is 90 and 1350 respectively. Oops. RESPECTIVELY. There. I was running out of room. All right. Please describe the relationship between the distance from the epicenter and the P wave arrival time. The closer epicenter is, the sooner the P wave can arrive. Using data from the sheet above, the closer epicenter, no, closer location had an arrival time of 12, 21, and 30 seconds. Second station. It took another, oops, TH, another less than a minute. Let's see, 35 seconds. 35 seconds to arrive. Whew. All right, so then it talks about using triangulation. So if you remember the conversation from before about trilateralization, which is how we find GPS locations, triangulation is very similar. So without reinventing the wheel or rereading this portion to you, I will just summarize it by saying that we use, you know, 3, actually 4, but we'll just say 3. Oops, that was a bad circle. Let me try that again. It's because they're all the same size. Okay. So here's our first place. So, you know, we now know that we are 1065 kilometers away and we're 1350 kilometers away from the second station, right? So we have one circle, but we could be anywhere along that circle, right? And then the same thing with the second circle, right? But now we can only be in 2 spots if we're in the same, like if the epicenter, if it's only one earthquake, it's going to only be in 2 spots. So then we have to have a third one. So I'm going to draw a really big circle there. And so this is where our epicenter is. That's what triangulation is. Now, the reason again that we need, the reason that we need, I just read your chat. The reason that we need a fourth one is to figure out how deep it is. So, so similar to GPS needing 4 in order to figure out elevation, it's the same thing. In order to figure out how deep in the earth is, we need a fourth one because we could be anywhere along that sphere. Of course, we're on the earth, blah, 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 right? So, all right, so now this time we're going to do something a little different. So, oh, oops, I skipped a page, didn't I? This is the next page, isn't it? Oops. Okay, that's fine. We'll do this. So I'll do like this one here. So what you do is you look at the difference between the P and the S wave arrival time. So the lag is 1 minute and 23 seconds. So 123, so that's 60 plus 23, so that's 83. And then I use the same formula I used before, so 83 divided by 8 times 120 is 1245. That's how you would do these. So, all right, now we got to this page. Sorry, skipped a page. So after this page should have been this page, and then we get to this page. Okay, so for this one, you only need to find one earthquake, and the reason why is the map's kind of small, and so and you're not going to answer these questions. The map's kind of small. I don't want you to have like a ton of circles all over it, and so you can either use the ruler to figure out where the circle's at, the paper ruler one. You could use a compass if you have one of those. But the first thing you have to do is figure out the time lag in seconds. So again, it's just like we did before. So let's see, 1, and then looks like 30. So that's 90 seconds, right? This time though, we're just to figure out the epicenter distance, we're just going to say time lag times 8. And the reason why is this map scale. You don't even have to. The map scale is 1 centimeter equals 120 kilometers. So, so we've changed the formula up a little bit. So I'm going to say warning. Check this. Not like other page, but kinda. And I say kinda because the map distance is actually going to be the divided by 120. So we're going to say 90 divided times 8 this time. So 90 times 8. So different formula. 90 times 8 equals 720 kilometers. And then we're going to divide by 120 to figure out our distance. So that would be 6 centimeters. So then we would draw a 6 centimeter circle from Portland, Oregon, if this is the one we want to do. Oops, here's my map. So here's Portland, Oregon. you can put the dot like in the middle of the letters, and then you would draw a 6 centimeter circle. So get out my little ruler here. I'm gonna draw a dot. And I'll come over here, draw another dot. Come over here, draw another dot. Come over here, draw another dot. Now you remember when I did this before, and I'm going to say it again right now. This is not the best way to do this. If you recall from my GPS thing, the best way to do this is to find which one is the smallest and start with that circle, because then you don't have like 50 billion lines. You only have, 2 billion lines. So here's my circle. Probably could have put in more circles here, but oh well. Oops. It zigged when I zagged. Okay, here we go. Something like that. So kind of sort of like that. So obviously, if you're going to use the ruler, you would put in more dots. Unless you're an artiste, in which case you could probably draw a 6 centimeter circle with only 4 dots. I am not that good. I still can't cut with scissors. I failed kindergarten like 3 times because I couldn't color in the lines. Okay, I wouldn't color in the lines, and I still don't know how to use scissors. So, all right, so that's the optional laboratory activity. So you can either finish earthquake 1 or you could do one of the other earthquakes. It's up to you. So again, here's my tip. Draw the smallest circle first, and then where the next circle is going to intersect. And I don't know where it intersects. I'm just going to make this part up. Let's say this was the smallest circle. So, or, the next one is in Boise, Idaho. So that's here. So maybe it's like here and here. And then the last one is in Los Angeles. So let's say it was here. I totally made that part up. It's not where the earthquake is. I'll be really funny if it was, but I don't think it's right. So, okay, so that's what you would do, and that's all you would need to do. You're not going to answer these questions here because you would need, well, you could answer this one. There you go. You can answer number 1, just not number 2 or 3 or 4. And that's it. So for the optional lab, you just need to do more of this, and it's just for practice. And we did the first 2 pages. So you would finish this, finish drawing this earthquake, or pick a different earthquake if you didn't, draw the earthquake, and answer question number 1 and turn that in, and you're done with your optional lab, which I would highly recommend and encourage, as I always do, that you do before you take the quiz. Okay, so any questions on the first page? Oops, not that page. This guy. How did we get a 6? Oh, the formula on the paper said the distance from the epicenter is the lag time times 8. And then it says divide the distance from the epicenter by 160 to determine the map distance. So that's how we got 6. So we did 90 times 8 to get this number, and then divided by 120 to get that number, because that's our map scale. That's so. So it's weird, and warning, Will Rogers. It's using the same numbers, but it's a different formula. So pay extra special attention to these parts right here, because otherwise this won't work out. You won't be able to draw anything on your map because all the map will be wrong. So It's different than these complete, I mean, uses the same numbers, but it's a different formula. And so yeah. But it's just to show you how triangulation works so that you get an idea of how it works. And on the test, on the final exam, I give you which formula to use, like which one I want you to use. So most of the time it's going to be, you know, using the one that we use for this part, which is the lag divided by 8 times 160. I mean 120, sorry. 160. I don't even know what I'm thinking anymore. All right. Any questions that I can answer for you? So we got a pretty good on this. You know, you got 2, 4, 6, 7, 8, 9 boxes to fill in for this part, and then probably about the same on this part. 2, 4, 6, 8, 10, 11, 12, 13, 14, 15, 16 if you do the same one, 19 if you do the other one. So again, shouldn't take too much time. And, you know, we are supposed to, you know, be actually physically meeting 3 hours a week. So, you know, hopefully it does not take you 2 hours to do the rest of this. Hopefully, I have my fingers crossed for you. Oh, and take a quiz. Oh, and that silly, pesky, actually, maybe there, oh yeah, there's a pesky quiz. Is there a pesky quiz? Let me look. Pesky quiz. No pesky quiz and no discussion. Dude, you people are weak sauce this week. Weak sauce. All right.